So TDD. They asked me to talk about TDD, and because we do TDD at Wicks, and we all love TDD. Yay, amazing. And I decided to talk about the problems in TDD, most specifically the problems that we have with build times. So TDD is very nice and everything, and it has a lot of benefits, but, and there's a big but, obviously. The big but is that there are maintenance costs associated with TDD, and as time goes by, they grow and grow and grow, and you have to deal with them. So before we start, I just have to say a few words about Wicks and such, because PR. So Wicks, if you don't know it or you don't work at Wicks, we're a global company. We have engineering offices in multiple locations: Vilnius, Kiev, Dnipro. Here in Israel, we have 2 offices, one in Tel Aviv right here, and the other one is in Beersheba. Currently, we have about 600 engineers, about 1,500 employees, I think more now. Yeah, no? How many employees do we have? More than 1,500 anyway. About 100 million users. We crossed the 100 million mark about, I think, 3 months ago. And about 500 microservices, about 550 last time I checked. So yeah, pretty big. Basically, not that anyone cares, because, promotion stuff. Anyway, so about me. Yeah, I hate programming. I really hate programming, seriously. But this is what I do. I really love it. It's kind of a love-hate relationship thingy. I'm weird, don't ask. So that's me anyway. Yeah. So, TDD. If you've read the book, and everyone at Wicks gets Goose, which is a growing object-oriented software guided by tests. It's a book about TDD, obviously. And the book basically tells you that the first thing that you have to do when you start a project is start from one test, one end-to-end test. And the goal here is to set up all the infrastructure you need to get this test to pass. And this means you have to set up the deployment system, you have to set up all the servers, you have to set up all the automation, and everything else you need to actually have a system that is able to run this test. So the point is writing the first end-to-end test and getting it to pass, and you need to set up everything in order to get this test to pass. Now this is kind of expensive, okay? The first test is the hardest thing that you need to do, because basically you need to set up all of those things. You need to set up automation, you need to set up all the infrastructure. It takes time. Test harnesses, matchers, everything that you need in order to get this test to run. And that's kind of a bummer, okay? But after you got past this first test, everything becomes much easier because you already have all the infrastructure set up. You've paid the initial cost. This is now a sunk cost. You can just start writing more and more tests. It's much easier. And this is really the point of TDD, because once you've gone over this initial hurdle, everything becomes much easier. And of course, once you started writing tests, you start always from IT and end-to-end tests, because they give you the most benefit. They actually test the entire system and not a small part that may or may not work when you integrate it with the rest of the system. So we have a preference for IT and end-to-end tests. Now, the problem, of course, with end-to-end tests is that they sometimes they can be too expensive, or sometimes you just can't have an end-to-end test. Why? It's very hard. First of all, think about a system where end-to-end means sending emails to users. We can't send emails to users, if it's actual users or paying users. We can't send emails to users every time we create a test. If billing is involved, okay, you can't bill a credit card every time you do a test. Although sometimes we can. And when one of the companies where I worked, we actually had a credit card that we used for testing, and we paid ourselves money with that credit card. We had about, I think, $5,000 that we used for testing. But as a general rule, you can't do this. So we compromise, and instead of doing end-to-end tests for everything, we do ITs, meaning integration tests. And that's fine. And then, once we have everything set up for ITs, basically we want to do ITs for everything, because this gives us the most benefit. And in order to do that, we try to make ITs as easy as possible. So we basically have automated dependencies. We automate whatever we can. We automate setup of MySQL and all databases. If we have Kafka, we automate that, and so on, so on, so on. In Wicks, we use embedded stuff. So we have embedded MySQL. We basically pack it as a Java dependency. It has the binaries inside and everything. All you need to do is include it in your Maven as a Maven dependency, set up a few lines of code, and you're done. You have MySQL up and running. It's very easy, very convenient. We use it for integration tests all the time. And also automated cleanup. So for example, you can just throw MySQL away, delete the database, and create a new instance of MySQL that is empty and sanitized and no problem. You don't have residue from the previous test. So it's all easy and fine and great. One problem, Jevons Paradox. So who heard of the Jevons Paradox? No one? One guy. Okay, two people. Cool. So the Jevons Paradox is basically a paradox that was coined in the Industrial Revolution. And basically, what happened was that they were using coal for the factories and steam engines and everything. And when a new steam engine was invented that was much, much, much more efficient in using coal, they expected the amount of coal being used to drop. Because if you have an engine that uses 50% of the coal that the previous engine was using, then of course you should be using less coal. Instead, the consumption of coal actually grew. We used more coal instead of less. And this is the Jevons Paradox. When something becomes more efficient or easier, we actually use more of it. Why? Because if coal engines use less coal, they are cheaper. And if they are cheaper, more people use them. So paradoxically, the fact that coal usage became more efficient actually drove coal usage up. Okay, many more factories used steam engines, many more vehicles used steam engines, and basically it proliferated everywhere. And this is basically the same with tests. If you make tests easy, you will write many more tests. And instead of reducing the build times, that if tests become more efficient, then build time should go down. Build time actually goes up because we write more and more tests because it's easy and it's fast. And this is a problem we have to deal with because we keep creating more tests. So longer and longer build times, but that's not the only problem. The second problem that we have is we start to get flaky tests. If we run tests in parallel, then often they interfere with each other and we get flaky tests. And even if we don't get tests that interfere with each other, sometimes tests fail statistically. If you have 10 tests and you have a failure chance of, let's say, 0.1%, you won't have a lot of flaky tests. But if you have 1,000 tests, chances are you're going to see a test failing every second build or second run. So that becomes a very, very big problem. Now, at Wicks, we use microservices. And microservices have a really, really big problem. I guess you can, deduce what the problem is, but anybody wants to take a guess what the problem with microservices is? Dependencies, yes, dependencies. So you write a service that integrates with two other services. How do you run IT? You need those dependent services in order to run your integration test. Okay? So you need to set them up somehow. You need to deploy them somewhere. So where do you run your IT?
Do those microservices not define a set of test doubles which they test themselves against?
That's one solution. There are many solutions to this problem. I've seen companies where they use staging environments to run tests. The problem is you can't use the staging environment for multiple tests at the same time. So you have a queue. And now you build basically waits for other projects to complete their tests. And then you have to clean up the staging environment and so on. So that becomes a big problem. Of course, those two services also integrate with two other services that integrate with two other services and so on, so on, so on. And some of them actually need data. Some of them need a lot of data. So maintaining such environments, staging environments or testing environments, that becomes a really, really big problem and can sometimes be very, very expensive. Think about a system like Wicks. we would have to have a staging environment with 500 microservices, and we can test only one project on that environment. So that's really, really annoying. So some people found a brilliant solution to this. They thought, how about we use Docker? How about we can, we put everything in containers, and then we just, take a laptop and pull up those containers and run the entire environment on Docker, because Docker is cool, and we can run anything on Docker and blah, blah, blah Docker. And yes, now they have another problem, which is Docker. That's really, really not a good idea. Okay? Why is it not a good idea? So first of all, I don't know if you tried running 500 microservices on one laptop. Yeah, I don't think it's going to run. Even 30 JVMs, probably not going to be able to run them on a single laptop. And you have to consider that those services have databases, and those databases sometimes require test data. Some services are data-bound services. They require a lot of data to function. If you try to run Elasticsearch with a lot of data on your laptop, probably going to run out of memory or CPU or I/O or whatever. Not a good idea. So we need some other solution. Now, another problem that we have today is that we integrate with a lot of online services. Think about Twilio or one of the Amazon services, one of the APIs, maybe Cognito, an API for machine learning or for image recognition or whatever. We need those APIs for tests as well. And we can't run those APIs on our laptop. So this becomes a big problem. So at Wicks, the solution that we use is, like you suggested, test doubles. We call those test kits. And basically, a test kit is a degenerate version of the real service. It's degenerate in the sense that it doesn't have dependencies. It doesn't have a database. Usually, we use an in-memory implementation of a database. So basically, we use test kits, and test kits are the degenerate form of the service. It has only the logic. It doesn't have dependencies. Doesn't have like a real database, whatever. We use the latest versions because this is how we test. We always want to test with the latest version, not necessarily the version that is deployed in production, but actually because we use Maven, we can hardcode the version so we can test against any version that we want. And this is great. That's very, very nice. The problem with this is that you can actually miss a lot of integration problems because this is not the real service and it doesn't use all the dependencies. If you have a problem that is caused by a third-level dependency or whatever, you're not going to see it in your tests. You're not going to be able to reproduce it in your testing environment. This can be pretty annoying, especially when you're debugging very, very hard integration problems. So sometimes we need a better solution. And the better solution is multi-tenancy. So a multi-tenancy is basically what you have on Amazon, where you can open another tenant of whatever service it is that you're using. If you're using SQS and you have a queue for production, you can just open another queue for your testing. And you can open the queue, use it for like a couple of seconds, and then delete the queue immediately after. And you could do this for all of the Amazon services, which basically means that when you're working with Amazon and you're creating tests with Amazon, you can actually use the real Amazon to test. You don't need test doubles, you don't need staging environments or any of that stuff. Or any of that stuff, you just use the real Amazon. And you have a lot of benefits when you do that. First of all, you're testing the real system. This means that your tests have more fidelity. It's high fidelity test. You can debug integration problems that you can't debug otherwise because, again, this is a real system. Okay? However, you have a problem with this. First of all, the testing environment is not sterile. What do I mean by not sterile? So on every production environment, you have statistical errors. You have statistical problems. I don't know of any significant production environment that doesn't have at least 0.01% errors. This means that you will have tests failing, not because of an issue with your code, but because of infrastructure issues. And that's kind of a bummer, really. The second problem is that you're basically bound to whatever version of code is deployed in production. So you can't test against arbitrary versions of code. In test kits, sometimes you want to test the version, the future version or the previous version because maybe you want to roll back or whatever. You can't do this when you're using multi-tenancy. And that's, again, kind of a bummer. But it's a limitation. Like anything in engineering, it's a trade-off. So another problem is that as time goes by and I write more and more tests, build times become longer and longer and longer. And we need to tame those tests. We need to keep the build time short, otherwise, we're not going to get anything done. So you know how, this is a quote from George Orwell's, one of his books, The Animal Farm. So all tests are equal, but some tests are more equal than others. So yes. And keep this in your mind for a second. We're going to talk about this in a bit. First thing you need to keep in your mind is that tests are code. And like all code, tests have to be maintained. There is a cost associated with having more code and more tests. And we basically want to maximize the ratio of features to code. We want to get the maximum features with the least amount of code. This is the ideal. Okay? Ideally, we would have a system running without any code at all. That's not possible in most cases. But if we could, we would do that. So the question is, how do we get the most from tests, but reduce the amount of tests? That's what we're dealing with here. And once we realize that, and we realize that not all tests are equal, okay, some tests give us more benefit than others, the question becomes, how do we identify which tests we can remove and which tests have more value and we should leave them or maybe put more emphasis on them? So there's a principle called proof-based testing, which basically means you have to ask yourself, what does your test prove? For every test that we have, we look at that test and we say, what does this test prove? Okay, so let me give you an example. Suppose I have a system, and that system is using libraries. And I'm testing a feature, and maybe that feature is actually implemented in that library. What am I proving by testing this feature? Presumably, this library already has tests. If it's a third-party library, maybe it's well-tested. So what exactly am I proving by testing that feature?
Consuming the API.
Sorry?
Consuming the library API.
Exactly. The only thing that I'm proving is that this library is wired, okay? That I have a dependency on this library, that it's loaded into my code. Yes?
That's true until you upgrade.
That is also true. But then again, when I upgrade, all I need to do is to prove that I have the updated version of the library.
If the logic changes when you upgrade, that test will fail, and that's conceivably good.
It's exactly what we're saying, is that you're consuming the API correctly.
No, it's not the API, it's the logic. You can consume an API just fine and get a different answer because of an upgrade,
but then you're not consuming it properly.
Yeah, that is true. There is a problem with APIs. Sorry? Yeah. There is a problem with APIs, and that is that most APIs do not have a good definition of behavior. Behavior can vary between API versions. That is true. Sometimes you need tests to prove that behavior hasn't changed. But as a general rule, if your test doesn't check that, then maybe you don't need it. So generally speaking, we have one IT that proves that things are wired, and then the rest of the features, we move from end-to-end or IT tests to acceptance tests. Why? Because we don't actually need to prove that the thing is wired. We don't need ITs to test the features. We just need feature tests that test the logic, the code, okay? In libraries or at the lower level, that's cheaper and easier to run. And we don't need to test all the features as ITs or end-to-end tests, which are very, very expensive. Now, the problem is that some bugs, like you mentioned, can only be tested by integration tests or ITs, or end-to-end tests. For example, let's say you have a library, and that library is supposed to do an RPC call, and it's doing this RPC call in a very, very weird way. Okay? Yes, you can prove that this library is wired. Maybe this library has tests that show that it's doing the thing that it should, and it's producing this RPC call, but it doesn't test a specific header, or it doesn't test, let's say, the size of the message or whatever. And you have a bug with this. It's an integration bug that unfortunately can only be tested by an integration test. So sometimes we have integration tests despite the fact that we don't need them, just to test behavior, like you said.
Which means that you don't need them.
Yeah, you do need them, but not to prove the library, not to test the feature, but to test something that is not covered by the test of the library or the logic that you have.
I'd say that if you have integration tests with the library, then their purpose is to document your assumptions about how this library works and how you use it.
Yeah, I think that's a very good way of putting this. Yeah, it basically documents your assumptions about the library. Now, of course, once you've done that, you also need to remember that tests need love. We constantly maintain tests, like we maintain code. We constantly refactor tests, we delete tests, we add tests, we change the behavior of tests, we change the implementation of tests, and we evolve them over time. In a lot of companies, they write tests once and they don't maintain them. And then you go after a few years, and look at the tests, you find a lot of redundant tests, tests that should not have been there to begin with, tests that should have been deprecated long ago because maybe you removed the feature or no one is using the feature. And sometimes you find tests that basically prove the same thing because maybe later on you added a test that already proves this. For example, if once we've added a test, an IT, to test a bug with the library, we've already proved with that test that the library is wired. Now we can erase the first test that only proved that the library is wired, because we have a test that already proves this. So for example, when you start TDD, you write one test that proves that the end-to-end cycle works. Usually it's a hello world test. It proves that the web server is up, that the database is up, that the server is running, and all of that. But once you wrote your first feature test, you are already proving that the server is up, the database is up, and all of that. So you can basically delete that first test. Okay? And this is the way we work. We constantly remove tests that we don't need. Yes?
What triggers you to go look for test removal? Is it something you do every day, every week, or do you have any way to know that the test that you're introducing now is a reason to delete an older one, or how do you know about that? When you start looking for test delete? What's the word?
So the test was, how do we deal with this? Do we periodically go and look for tests to remove, or do we have some other way of doing this? So this depends on the team. In my team, for example, we don't have like a periodic cycle for doing that. Every time we look at the code, every time we look at tests, every time we have a feature, you know, we're already in the code, we're already looking at the tests, and when we implement a new test, we go and look at the other tests, and we ask ourselves, okay, can we remove those other tests? Sometimes someone would go and refactor tests on purpose because maybe they have some time, some free time, maybe they dealt with the test in the previous time when they implemented the feature, and the tests were too complicated, and they want to make them simpler, and so on. So it's usually triggered by, you know, some kind of a feature or some kind of a bug that we worked on previously. Okay, we don't do this periodically, but it turns out that we do this all the time, so we don't need to do it periodically. And one more thing that we do is we refactor tests to use the same infrastructure. So we basically create one global test environment, and all of our ITs inherit from that global test environment. And this makes things a lot simpler because whenever we add some dependency, whenever we add a matcher, whenever we add a feature basically to our test harness, all the ITs basically can use that feature, and it makes all the tests behave in a similar manner, so to speak. So, final thing I want to talk about is using information theory to minimize the amount of tests you run. A lot of people have really, really long build cycles because they have a lot of tests, but they actually do need all the tests. All the tests prove something meaningful. But do all the tests, whenever you run them, provide the same information? And the answer is no, they do not provide the same information. Basically, we are interested in failing tests. We're not interested in tests that always pass. We're not interested in tests that pass even now. They don't provide any information. We are interested in tests that fail. This is the meaningful information. We want to know that something is not working. Okay? So what if, by some magical way, we could only run the tests that fail? The problem is we don't know in advance which tests will fail, and this is why we avoid this. But there are ways in which we can guess. We can make educated guesses about which tests might fail, and only run those tests. So we could take statistics. We can take, let's say, all the test runs we've ever made and see which tests fail and which do not fail, and do statistics on that, and based on the statistical score of the test, run tests that are likely to fail.
It's reverse Darwinism.
Yeah, I know. In a sense, it's reverse Darwinism, yes. Another way is to look at the commit and run tests that actually pass through this code. Coverage engines, tools that measure coverage, they know which code path tests have been through. So you take this information and you look at the commit and you see, okay, if this commit touched this file, let's run all the tests that go through this file. And then you run tests that are more likely to check the thing that you have updated. Okay? And of course, the problem with this approach is it's not deterministic. It will not catch all the bugs. So the way to do this is you run partial test suites when you do commits or when you push into the repository. But before you GA, before you do the final deploy, then usually you would run all the tests that you have because you need to verify and you need a much higher level of confidence. Yes?
Just one adjustment. If you go that route, you should probably also have a schedule, like a nightly or hourly or whatever, full-blown test run. Otherwise, you will hit the issue at exactly the least convenient moment.
Yes, that is also true. Usually, yeah. So the comment was that if you go that route, you should always have some kind of a nightly full build. Run periodically the full build, so that you don't hit the failing test at the least convenient time. But if you're doing CD, then you have a GA running probably every day anyway. Also, the idea is once you have a failing test from the full build, you start a binary search in order to pinpoint exactly where things broke and actually find the commit that broke the build. So basically, it's an optimization. It doesn't mean that you don't run the full build ever. Yes?
Isn't the problem that mostly the failing tests fail on the devs machine, on the developer's machine, not OCI?
You wish.
Well, yeah, obviously sometimes. But most of the times, that signal that a failing test is failing and gives you more information, happens on the dev machine.
So last time I did this, we actually only used statistics from the CI machines, from the build cluster, because we didn't trust the developer machines. Basically, when you do this kind of statistics, you want to have something that, let's say, is more sanitized. But yeah, you're correct. But most of the developers that I work in Wicks, anyway, when they implement a feature, they run a partial test suite because they already know, what tests are likely to fail or which tests are more meaningful, because they know that they worked on a feature in this area, and then they submit they commit, they push, and the RCI system runs all the tests. So it's basically the same idea. Yes. So the question was, is there a way to mark tests as being more important and making sure that they always run? So yes, there is. Most of the test harnesses that I know, like JUnit and so on, allow you to mark tests with tags or annotations and so on, and you can configure those in your build at build time and run the full test suite or just the important test suite and so on. So I've kind of run out of time, so we're going to skip QA. So thank you very much, and I'm going to give the mic back to Tomer.